you gonna say
Are we all dry? Testing. You know, the Chippy mascot is a chipmunk, not a squirrel. Sorry. LaSalle Network, man, they are putting this together. They're hosting, and they bought the food as well and the beer. There is beer in the fridge if you go in the back. It's called HVAC beer.
I love the
squirrels are trying to get at it. I have to tease this guy because he's charismatic. So we got a great meeting lined up. Happy New Year's, everyone, by the way. Chippy's alive and well, obviously. We made it through the snowstorm here, or maybe we're all stuck in the city. We can't go nowhere. I don't know. And, but we got a great lineup tonight. We got our acclaimed David Beazley at thebees.com. Tweet him at, or tweet him. You know, I can't even tell you all the things he's been involved with Python over the years. It's really astounding. I mean, it's really wonderful to have him here to talk. And, it's not going to be probably the most downloaded video this time, unless we just get amazing video from our professional crew that was highly debated its value on the Chippy website. I should have probably intervened when I was in Japan at the time. Whatever. It is worth more than zero, I'll tell you that right now. It's very helpful to people out of town and people who want to keep up to date with us. I kind of, it's a double-edged sword too, because I'm always kind of like, well, why come to the meeting if you can just watch it online? But I'm glad you did make it here, and hopefully it will be entertaining for you. Our second speaker is telling us about something he hates. Is he here? Is he here? And he has a Pypy background too, so I think there's another like Pypy theme that isn't really being spoken here. Really here? There's some Pypy associations going on in the atmosphere, because our Python, isn't that Pypy related? Pypy related. Okay, thanks. He doesn't know. His brain's gonna explode here shortly. And so we got a great video. I want to give a warm thank you and welcome to Rob and LaSalle Network for listening.
Thank you. Thanks, everyone. Some of you I've met and had the chance to introduce myself to. Some of you I haven't, so welcome. Thanks for coming, especially grinding it out in the snow. I know it's pretty bad out there, so be safe when you drive home for sure. LaSalle Network is a staffing and recruiting firm, and I actually specialize in the technology recruiting group of our organization. And one of the areas that we've identified as we went over 2012 strategy is just to understand more about this community. So we're here to learn. I'm just here to witness and take a look at what all of you can do, and it's very specialized, and I really appreciate the opportunity just to sit here and be a part of the conversation, and hope that the speakers, thanks so much for coming today, and just look forward to taking a seat and being involved. So thank you, appreciate it.
All right. All right, this. I don't know. We'll see how this talk goes here. Just as a disclaimer, this is like, I don't know, it's work in progress. So it's kind of nebulous. I'm sort of thinking about how this relates to a Python talk. How many people have messed around with Python? Just curious. Okay, so I've been kind of looking at it lately. I have not. I'll sort of admit that I've not done a lot with Pypy. I've run it a few times, kind of tried it out. I'm sort of aware of it through the kind of the conference scene and blogs and stuff like that. Sort of recently been trying to wrap my head around what's going on inside of Pypy, and that's what this talk is about. So some things that you probably know about Pypy, unless you've been living under a rock or something. It's basically Python implemented in Python. Okay, so it's like a complete implementation of Python interpreter in Python. It's apparently quite fast at a lot of stuff. if you run it, it can actually be significantly faster than CPython. I mean, I've done a little bit of experimentation with that, sort of found that for certain things it might be 30 to 40 times faster than CPython. Other things, maybe it's like 10 times faster, but it is fast. A lot of smart people working on it, like Alex over here. But if you ask people how it actually works, from my point of view, it's total magic. I mean, it's like, I don't know whether there's like magic, whether there's like crushed up grad student souls in there or something. You know, what makes it work. So, and just to be a little bit honest, it kind of scares me, just a little bit. Not the concept of Python and Python, but just the implementation of it seems a little bit forbidding. I don't know, those of you who have looked at it, have you kind of looked at this code for it or anything? Or you just kind of download it? It's a pretty hairy thing, and I have this, this question. I was like, can I actually even understand what's going on in there as sort of a, an outsider, because I've not contributed anything to Pypy. Can sort of, normal programmers understand it? Like somebody who has like a solid background in programming understand it. Can you debug it? Can you modify it? I don't know. And one of the things I find really intimidating is the process of building Pypy source. You're probably not going to be able to see this very well, but if those of you who have tried Pypy, have you ever built it from source code? It's this really crazy thing. Actually, I could probably do it in the tutorial later just to find it here. So if you go into like the Pypy source code, the way that you build the thing is you have to go into sort of this deep down into the hierarchy. And then what you do is you run this like translation script. So you say, okay, we're going to translate. I'm just going to run translate, and then you give it some options, like I want the JIT or something. And this thing will go off, and it will just, God only knows what it's doing. It starts running the C compiler, doing like, do you know what's going on with this part of the platform check stuff? I'm going to ask Alex as the go-to expert in Pypy.
Yeah, basically it goes to C compiler. This is sort of the same way a configure script would. Yeah,
okay.
Size and stuff.
So it's just trying like different configure options and so it kind of cranks away, does some C compiler stuff for a while, and then I don't know, I'll give it a minute here, and then it will basically proceed to crank away on stuff for well over an hour on this machine. This is a quad-core modern MacBook with 8 gig of RAM. It'll take about an hour, 20 minutes, or something like that to sort of run through it. I actually made a little movie of it. See this here. This is a movie of building it from source that I'm going to start here. And you're going to look at that and you're going to say, I have the fastest computer in the world, if you've ever done Python. This is what it prints up when it builds. It makes like Mandelbrot says. It goes up. That's actually running at 64 speed, 64 times faster than normal. So this is going to compile Pypy in about a minute as opposed to like 75 minutes on my machine. But the question that comes up with that is that first of all, you need quite a bit of memory to do this. I have like an 8 gigs of RAM. I've done this on machines with less, and it took like 14 hours to build.
Finished?
It did finish, like on my laptop, before like a regular MacBook, took like 14 hours to build. Takes a lot of memory. What in the hell it's doing over here, I have no idea. I mean, with like all this Mandelbrot set stuff and C compiler and warning, and it's just like blasting away for like a long time.
Is he using all the cores?
No, it's just one core because of the GIL. bring the GIL. You got to bring the GIL into everything. So that's here. Okay, so now it's writing out C code. You can see the memory on the machine is like way up there. Actually, I missed that. Okay, so 4,500 seconds later, you now have like a Pypy interpreter. So that's what it looks like to build from source. I mean, it's like this very intimidating thing. I look at that and it like scares the hell out of me a little bit. It's like, what happens if it breaks? I mean, it's like, do I have any hope of fixing it? So there is that, and then there's just this other thing that I think about, and this is just my own opinion. I think like a big part of Python's success is actually the fact that people can tinker with it. Like if you go to CPython, a lot of people can mess around with that. I mean, it's like written in ANSI C. People know C. It uses make files, and it's documented. It's something that's accessible to the program. You can mess around with it, do stuff. And as you know, I mean, there's a lot of documentation on CPython, the high-level stuff. But you can also go pretty low level. so forth. If you jump into Pypy, or before we jump into Pypy, I actually think this stuff matters in the big picture. Like the Pypy guys, they want people to use Pypy, adopt it and things with it. I think that stuff kind of matters because as a user community, you want people to submit bug reports, you want people to make extensions and to port it and to play with it, and like all the stuff that comes into Python, I think a lot has come about because people are tinkering. And so part of my motivation on this talk is actually just to kind of see whether you can tinker with Pypy, kind of the status of that is, whether that's something we're looking at. And if you go into Pypy, you will find that it's quite a different flavor to it. My own impression of it, it is sort of an advanced research project. A lot of the documentation on it is couched in sort of academic papers, conference papers, journal papers, a lot of presentations. If you go to PyCon, you see these presentations where it's like, oh, Pypy is really fast, and they show lots of benchmarks, but they don't really take you that much behind the scenes as far as like an implementation side of it. So fair amount of documentation, but it's not really very low level. Some of the high level documentation and stuff like this, they'll show you these like flow graphs of like, oh, it takes source code, it does this to it, and, oh, it just annotates it, does that. There's a whole lot of detail missing from that, like what it's actually doing. You can go to the tech reports. Really, if you can't read that from the back, you won't read it any better. But this is like from one of the EU progress reports on Pypy, and I'm looking at that. It's like, okay. In their defense, they have to write it like that. Pypy is basically like a funded research project in programming languages. And if they don't write it like that, they're not going to get funding. So I can cut them a little bit of slack on that. Actually, I think like the academic programming language community makes Hacker News look like amateur hour when it comes to like funding people. So there's that. The other thing you could do is just look at the source code. I don't know. That's its own adventure as well. So it is a little bit difficult to get into. And so what I'm hoping to do here is actually just kind of take you into a tiny bit of how Pypy works, and mainly just talk about the implementation language. There's this implementation language called RPython, and I've kind of been tinkering around with it. And really the whole motivation is just to look at it because I'm curious. I haven't done anything with Python, RPython. I'm not attached to that project. I haven't used it for any real project. I know of it just from the Python community. I know there's a lot of buzz around it. I know there's like some amazing things that people have done with it. So that's kind of my motivation here. Actually, the only thing that I've done for Python is I submitted a bug report about the guild because it's my duty to put guilds everywhere. So that was my one submission. So just as a little bit of overview, if you've not done anything with Pypy or you don't have to see much about it, it's basically an implementation of the Python interpreter in Python. Just to kind of give you an analogy of it, the Python that you're used to, like CPython, you have Python program, like Fibonacci numbers or something, and it runs on top of a Python interpreter, which is written in C. You can download the C code from Python, it runs the interpreter. Pypy is basically that same idea, except that instead of having the interpreter in C, it's written in Python. Okay, so you have like Python running an interpreter for itself, essentially. And one of the things about Pypy is that you can actually run it as a normal script if you're so inclined. It's Python code. So if you want to, you can actually just run the Pypy interpreter as a Python program. It sucks. If you do that. It has horrible performance. I haven't measured it. Do you have any idea?
It's like on the order of 2,000 times slower.
Oh, 2,000 times slower. You'll notice here that it took like 35 seconds just to start up at the interactive shell.
Can you clarify that? You
What?
run the Pypy interpreter as a program in the CPython interpreter, so you actually make a script on there too.
Yeah, you just run it in the Python
So you run the
interpreter.
Python,
So like,
Pypy and script.
yeah, it's just a script. So let me get out of here. So I think it's in like the directory of the distribution. So there's a script py.py. I haven't really looked at that in great detail, but okay, main entry point to the Pypy interpreter. you can just run it. So like if I type Python, it's Python 2.7, that's C Python, and you just type Python py.py. Now again, it runs the C compiler. I don't know what it's trying to figure out with that. So it does a whole bunch of little setup here, and then it kind of sits there for like half a minute or so.
Why did you C compiler at all?
Don't ask me.
Because-
I think there's some configurations
Yeah,
there.
basically all that configure stuff that is at compile time when you compile it, it's really just like a bunch of global declarations, so it gets invoked when you run it as a script as well.
I thought the whole point was not to have to, I thought the whole point was to do it in Python, not in C.
Yeah, it's still all Python code, but like we interface with C libraries, like for the select module, interface with a bunch of C libraries.
Why you need to compile?
Basically to verify like the sizes of structs and other things like that. Because when we interface with a C library, we have, are you familiar with the C-types library?
Yeah, okay, so I understood that part about getting sizes of the,
Yeah.
like the ink could be a different size or something.
Yeah, stuff like that.
Yeah. Well, I mean, I think also running Pypy like this is not really the intended usage of it. Like you would never, like who would want to run Python running on top of Python that's like 1,000 times slower than Python. It doesn't make any sense. So, but I think the main point is that Pypy though is implemented in Python. So I mean, it's a Python program. If you run it on the Python interpreter, it will run. Now you might not get some of its features, like probably I don't think that JIT runs in this mode or anything like that, but it does run. You can probably mess around with it. But that's not really what people do with it. So what actually is going on underneath the covers is that Pypy is implemented in this thing called RPython. Okay, quote RPython. One thing about this RPython that, I mean, unless you've looked at Python, that's kind of confusing, is that RPython is not Python in any traditional sense that you might think of. In fact, it's not an interpreter, for instance. Like there's no they don't run some program called RPython. It's not an executable, it's not an interpreter, it's not anything like that. Essentially what it is it's just a subset of the Python language. So take all of what you know about Python and then carve out this tiny limited subset of it. That's what RPython is. I'm going to talk about what it is, what you can do with it in a second. But it's essentially valid Python code, but restricted in what it's allowed to do. And that's actually about the only similarity. Essentially, what this RPython is it's, for lack of a better analogy, it's like C++ in Python. It's essentially Python syntax, but you actually have to compile it like C, C++, or Java, and it does static typing like C, C++, and Java. It's all done through type inference instead of type declarations, but it's essentially a statically typed language. If you love a lot of the dynamic features of Python, like being able to put anything you want in a list or anything you want in a dictionary, you will hate RPython. It's like, it is not dynamic at all. We'll get to that. Yeah.
What does it compile into?
C.
It compiles into C. Sweet.
Yeah.
That's why you need.
Unless I've missed something.
In theory, you can also compile into like JVM bytecode.
Yeah, let's not go there.
How would you do that?
Probably the closest thing that I've used to RPython is ML. I mean, it's been quite a while since I've used ML. I mean, has anybody used ML in like? Yeah, I mean, used it in school. I mean, it was. Yeah, my impression of ML was like this really cool language, but you could never get anything to work. Like what you would do is you would just code for hours and hours and hours, and you'd like get these like code type error, code type error, code type error, type error. You'd have like 5 hours of type error, and then like magically all the type errors would go away, and your code would fly. Like you get the right answer, but it didn't go lie. Is that kind of like your experience with ML?
Going from Python to ML is quite alternative. It's really like ML in the sense it's like functional. It's not Python at all.
It's not. Well, I wouldn't go that far, but the
feel of it.
The feel of it felt very ML-ish in the sense that if you had any mistake in the type system, the whole thing would just go belly up. Not complain. So what I wanted to do is actually show you just like an example of how you write RPython code. There's actually just a little bit of stuff you need to do it. So So I'm just going to do like a hello world program in RPython. Okay, so we're just doing hello world. What I've got here is this is almost exactly like a main function from C. Like if you write say C code, you have to have a main. Main has to take in an argument list, and it has to return an int. Maybe bringing back forward memories or something like that. But the signature of main in C is int, and then you have like the arguments there. So I have like this hello world program there. To use RPython with Pypy, you only have to write this one function called target. And all it has to do is return the function that is the entry point to your program. What this is doing is it's just telling RPython what the starting function is.
Is none the arguments?
None, I think, is some options, I think, I haven't really looked into that.
I want to say it's like an optional like compilation policy, which is deeper magic if anyone ever needs.
Yeah, just none is deep magic, don't go there. So that's basically an RPython program. Hello world, return that. Now the question is, how in the world do you run that? So if you're normal Python, you would do something like this. This is like Python 2.7 kind of stuff. Okay, so this is like CPython. So if you wanted to run this in CPython, you might just put like a little main program on it, and then what you would do is just type Python hello.py, assuming that I saved it in the right directory here. Let me move it down one directory. Okay, there's hello. You can run that. Print out hello world. To do this with RPython, it has to be compiled. Okay, so RPython is not an interpreter in the normal sense. What you have to do is basically compile it, and the way that you compile it is you run it through this translate script that comes with Pypy. So this is part of the Pypy distribution. There's sort of this translation tool, and what you do is you say, okay, translate hello.py. It's not going to take an hour, but it does take a little bit of time. So
That's truly fantastic.
it's really fantastic.
Does it take that much time each time?
Yeah. Okay. So 17 seconds. What it created is basically a program hello.c in your directory.
It was the fastest hello.
Yeah, the hello C is a 190K file. Yeah, it's got the garbage. It's garbage collected. Okay, so, and then you run it, you get hello world. That's basically our Python.
That was fast.
Really.
So you like all the output from that?
Well, it boggles the mind a bit to wonder what it's doing there, but.
Well, that's what I asked. That's what
Please.
this, yeah.
Do the
Yeah.
Python people or do the CPython people define the RPython subset?
No, I think the Pypy people are defining that. And it actually doesn't seem to be all that formally defined. It's a little crazy there, but that's kind of an example of it. And then you run the translator, and it does a whole bunch of output. There'll be a quiz later. If you wanted to do a more complicated example, I mean, you could run like the Fibonacci numbers or something. So this is just partly because the Fibonacci numbers are so critically important to everything here. Yeah, Node.js. Well, if I were doing Node.js, I probably have to do this with like an async callback. Well, let's not go there. So here's sort of another example. It's just a program that's going to compute like some Fibonacci number, doing a really horrible algorithm on it. So we can try this one. Let's translate that, just so you can watch the process again. It's pretty. So
It's like downloading a whole GitHub
Yeah,
repo
yeah,
there.
like a whole Git thing. It really is impressive.
It is.
The amount of output and the intimidation factor.
Every step there is probably critical.
Yeah, probably critical for the whole. Yeah. So so you do that, and we can try this out. Let's try I'm gonna just do a timing test of timing. This is just gonna be the normal Python version of this. So let's compute the 38th Fibonacci number to see how long that takes. I don't think it takes more than an hour or so.
We'll see.
There'll be a quiz on the compilation process later. Okay, so that took about 20 seconds to do that. Let's run the RPython one that we made with that.
Don't forget the time.
Well, we already got a sense that it's a lot faster. Okay, 0.49 seconds. So you're looking at basically factor 40.
How ugly is the C code it produced?
I don't know because I don't know how to look at it.
Oh, it doesn't give you that.
I haven't gotten that far in my.
Magically.
Do you know? You probably know how to look at it.
I don't know wherever a temp directory, it can say somewhere now that all that output actually
Where it goes, but I think it probably deletes it out.
No,
It
the
doesn't?
last, I think 5 by default are saved.
Yeah, okay.
C code's ugly though.
I'll bet, yeah. Anyway, if you do this, it is pretty fast. I actually did a timing of this RPython against ANSI-C. It's not that far off, 2.1 seconds versus 2.6 seconds. It's moving right along because it is compiling C code. Now, what's going on underneath the covers of this is going to kind of take us into behind the scenes a little bit. One of the reasons why this runs so fast is that RPython is basically statically typed Python. It's like C code. You pin ints and floats and things. The way that works is that it's doing some type inference on your code. Just to kind of give you an idea of that, if you have this Fibonacci code, it looks at it and it will say, you know what, you're calling Fibonacci with an int. You just look at it, right, their main, you're calling Fibonacci with an int. What's going to happen is that int is going to propagate through your code. So it will know, okay, the argument to fib must be an int. And then it's going to look at the source, look at the body of Fibonacci, and it's going to say, well, that's an int. It returns an int. So the return type of Fibonacci is an int. And essentially what's going to happen is the whole code gets annotated with type. And the whole thing is ends up being statically typed through this kind of type inference technique. And so that's why it's fast. But one consequence of that is that you actually lose almost all of the dynamic typing features of Python by doing this. And I'm actually going to show you some examples of this. So one thing that you can try, let's just go back to the hello program here.
So if you had called that Fibonacci function twice with once with an int, once with a float, is it like templates in C++? Would it generate two different versions of it?
I think floats are a little. It might die, but you have to try that. What we can do though is it's kind of, let's say you have an add function.
Yeah, I mean that's a perfect example.
And you said print add 2.3, and then you said print add hello world.
Yeah.
Like that. That actually is perfectly fine in Python, right? That's it's dynamically typed, doesn't care about it. That will blow up in RPython. So if I try to translate that, it will sort of work on it for a little while, and then it will just blow up with a huge error message.
It drops you to PDB.
It drops you to PDB, actually, yeah. Version of PDB. And you kind of have to read through the error, but it's basically getting tripped up because you're calling the function with two different signatures. So that first function call is essentially the signature. So if you called it with ints, that's what it is. So you don't get any dynamic typing on function calls. So
I think it would split it into 2 methods.
That's what I would think.
not that I'm aware of. Do you know what the
No, if you want something like a C++ template to be or a Java's generic, so it's like a generator that lets you say, I want to use this way. By default, it assumes that you have a single set of types for each method.
Yeah, it's very much statically typed. Some other restrictions of it: all the container types can only have a single type in there. So if you had a list of numbers, that's okay. But if you had a list that had a number, a string, and a float in it, forget about it. You get an error generating that. Same thing for like dictionaries. Like if you have dictionaries where it's all the same kind of data, like string keys, string values, that's fine. If you had values where one of them was a string, one of them was an int, it'll blow up. And really kind of the right mental model on it is to think of C code. It's like, with C, you have to have the types. Like in C, you can't make arrays really of like mixed types. You have to declare like a type, and that's what this is doing. Same thing for like classes. If you had like a class pair, for instance, self X, self Y, the types of those attributes would actually get fixed by the first use of it. So if you say pair 2, 3, it's going to go in and say, oh, those are ints. And if you try to assign it to strings, it's going to blow up. So it's really kind of a weird programming environment in the sense that you don't have the dynamic features of Python. I mean, yes, it's Python syntax, but it is not at all like Python as far as like these semantics.
And what else?
You get
So
tuples.
as opposed to using C directly, this gives you sort of primitive high-level data structures, and that's probably.
You get high-level data structures, and probably one big thing you get is garbage. So like, not implementing it, like if you had to implement it in C, then you have to write your own garbage collection.
Memory allocation.
A big mess, but it's essentially you get like a core set of data types. I think you get tuples, lists, and dictionaries. I don't think there's sets.
There are not sets.
Okay, there's not sets. There's actually a whole bunch of missing stuff as well. Like you can't use generators. A lot of the special methods. Yeah, some of the special methods don't work.
The only special methods that work are under, and under, down.
Okay, all the other ones are.
Calling out to external systems, you probably get into this pretty much.
Nah, probably not.
No, okay, so then calling out to the Python libraries or C libraries, is there any sort of candy for that, or is that just not possible?
Yeah, RPython has its own foreign function interface for calling out to like C or Fortran or whatever.
Yeah. Yeah.
How does it infer its return type?
I think by what you just passed to the return statement.
Right, but if you have multiple return statements that return different types.
Or if you just
Well,
return
my guess is that it would find the first one during like some kind of annotation pass, and then it would raise an error if you had mixed, like you got two returns that had different types. So it would eventually just go belly up, saying, "Hey, I know what you're doing." One thing that gets a little bit wild with RPython, I don't know how much I want to go into this, but if you want to create data structures that have mixed data types, like let's say you actually wanted to have a dict that had like a string and an int in it, only way that I could see to do that, and Alex can correct me, is to basically do boxing of values. And kind of the idea on that is you basically make like a base class that just says, okay, this is some value. And then you specialize it with like an int version of it and a string version of it. So you say, here's an int value, okay, some class. Here's a string value, some class. Essentially what will happen is you make your data structures hold instances of those types, and they will unify under the base class. So RPython will say, oh, this is a dictionary mapping keys to some value object. Problem with that is that you have to essentially go through method calls to get into the internals. Like if you want to pull a value out, you have to call a method to do it. Similarly, if you want to store something, you have to wrap this class around it. So that's something that you have to do. Now, just as a few notes on this, if you read a little bit through the Pypy docs, the developers of Pypy seem to be somewhat adamant that users, especially like just casual end users, should probably not mess around with RPython. And I would, having looked at it, would tend to agree. I mean, it's not anything like the Python that you know about, other than like the syntax is the same. Semantics are quite different. There's a number of like really annoying things that it doesn't let you do. It's great for maybe implementing Pypy, but it's kind of its own thing. So that's one thing to keep in mind. One thing I worry a little bit about is, so I used to do a lot of work in like scientific computing, and I worry a little bit that scientists are going to look at RPython and they're going to say, ooh, it's almost as fast as C. I'm gonna go write, like molecular dynamics in RPython or something. I actually tried that, by the way, last week just to see what would happen, and it does run quite a bit faster than Python. It's 40 times speed up. Doing that, but I was frankly quite annoyed at the code. Like I was actually cursing at it because of like things that were missing from RPython that I wanted to use, like like iteration protocol or something. A lot of things that I wanted. So the final little thing I want to do here, let me see how I'm doing on time. I wanted to just say a little bit about what in the world is going on in that build process, like with the screens of the code. In hindsight, I'm not sure that I should have looked at this. I mean, I like last week, I was like, oh, I should go figure out what's going on with translation. Turns out that this is just diabolical, what's going on in there. I mean, essentially when RPython takes your Python code and turns it into C, it does it without doing anything normal, like a compiler. At least that's my take on it. I mean, there's like no parsing, there's no like traditional operation of a compiler. Essentially what it's doing is it's operating entirely off of a sort of a live version of your code that has been imported. Like you take your Python code and you just import it into the interpreter. And this is like CPython, keep in mind. It's just like you type import, you bring all of your code in, and the entire translation to C is done by looking at the bytecode of your live program. Now the way that just to kind of give you an idea on this, every bit of Python code that you write is compiled to bytecode by the interpreter. This is often not seen or by a lot of users of Python, but this is actually what happens under the covers. I mean, if you're in the
So is that the same bytecode for all the different backends? Java,
Yes.
well, we're talking about CPython right now.
Okay. But
So we're just in, yeah.
But that's the whole point of Pypy, isn't it? That you can that it reports
This is
all
a
the
C
different
Python
backends.
bytecode.
Yeah, this is just
Not
CPython.
necessarily
So,
shared by other vendors.
so one of the things that's bizarre about it is you basically start from like CPython, but you're going to hoist this thing up into RPython and eventually into C. What happens is when you write Python, one of the things when you write Python functions, they actually do get compiled into low-level code. There is a library module called dis that will show you the disassembly of that. Okay, it's not very interesting for the add function, but it'll basically show you the sort of the low-level bytecode. It turns out that RPython is operating exclusively from that to build a C program. It basically takes your code it basically imports your code, brings the whole thing in, and generates C code straight from the bytecode.
So is it like doing a bunch of comparison on binaries? Like if some crazy binary then generate this C code?
What do you mean like a crazy binary?
Well, this is in Python.
It's in Python.
So
yeah.
then looking at bytecode, so you'd have to say, you'd be inferring some like abstract syntax to know this is, how are they matching on that? It must be an if statement.
They're just literally, okay, so, yeah, I'll see if I can explain it. So, they're going straight from the bytecode on functions. Those of you who don't know, the bytecode is available on a function if you go to the code attribute. And if you go CO code, it's literally a string.
So
of
they're
bytecode.
dealing with that though.
That is what they're dealing with.
Yeah, that's what I'm asking.
That.
Yeah.
That. So,
Like if /x02 then generate some other thing. Like that's what their code looks like.
that's what they're working from. Now, they're not even trying to take it back into source code.
No, it's like the C.
Yeah, go to C. Yeah, they don't go directly to C. But that's what they're working with. They're working with like the bytecode. And there is a lot of information underneath the covers, like the code attribute, the names of variables, and all sorts of other stuff. And RPython is basically working with this. It's not working with source code. It's working with that. Everybody still with me? The head explosion part. And so what happens here, and this is where my head starts to explode. It turns out that one of the pieces of Pypy is a bytecode interpreter in Python. Keep in mind that Pypy is Python implemented in Python. So as part of that implementation, there is a bytecode interpreter that runs bytecodes, okay? And it's written in Python, because that's the whole point of the project, is to write everything in Python. So it turns out that there is this bytecode interpreter inside of Pypy, and the way that that has been implemented is to be modular. It turns out that it's kind of this modular implementation where you can plug in objects into the bytecode interpreter. Okay, so what happens is this RPython thing takes Python code objects from CPython. Okay, so keep in mind we're in CPython here. and it actually interprets them using the Pypy bytecode interpreter in Python. Okay, so it's like, there's already like too many levels of Python. And so what it does, it actually interprets your code using the Pypy version of the bytecode interpreter. And then it actually records what it sees. So there's actually a recorder underneath this covers that is recording what's going on. And it uses that to build a representation of your program. I'm going to kind of take you through that. This is, the font is small and it's not going to diminish so essentially what's going to happen is you have this stream of instructions. This thing gets executed in sort of what's known as like this abstract interpretation. It's essentially, it's going to run through the bytecode and it's going to look at what it sees and it's going to build this sort of graph of what's going on. The way that it's going to do that is it basically starts by creating like a block, saying, okay, here's a block of execution. There's a certain number of inputs to this function. Turns out that the inputs are just coming from the function here. There were 3 inputs to that. And what it will do is it will start basically executing instructions in the abstract, and it will monitor what happens to the stack frame that's associated with that. So it actually starts executing instructions, sort of manipulating the internal stack frame attached to that thing. Okay, so it's sort of it's kind of like an emulated execution. And then what happens is every single time it hits actually an operation of interest, like add something, like add 2 numbers, it actually makes a new block representing the execution of that one operation. And then it just sort of keeps going with execution. Okay, so what it's doing is it's sort of recording instructions in these blocks, and then it starts chaining blocks together. Okay, so like sort of recording what's going on, and so forth. And sort of every bytecode operation actually gets its own dedicated block of execution. I'm sure everybody's head is completely exploded. That's why.
It's just deducing the block structure.
It's deducing the block structure, yeah. And then you get into some really weird stuff is when you start doing like Boolean jumps, like if conditionals and things like that. If you have these like jump operations, what ends up happening is the interpretation actually has to take both branches. This is really bizarre. Like in a normal Python program, you only take one branch. In this interpretation stage, it actually takes both branches at the same time, essentially. It follows them both. I'm not going to say how that works underneath the covers because it's utterly insane. But what ends up happening, though, is that the thing will basically follow the false branch for a little bit, do some instructions there, and then it will go up and work on the true branch for a little while, do some more instructions there, and then it literally will sort of follow both the true and false branches, kind of interweave with each other until they join up at some point. So, it sort of works through your code, building these like blocks. Eventually, after like massive head explosion, you will end up with sort of a graph, like a flow graph structure. It looks something like this. So you're going to end up with all these little tiny blocks, where every block is basically a single Python bytecode, or a single operation, like add, subtract, multiply. From there, it does a little bit of simplification to not have so many blocks. Does that. And that's actually just the first step for the rest of the interpretation problem. So if you look at that, like those screens of code that are going by, that's basically what it's doing underneath the covers. It's literally working off of like the bytecodes and like doing sort of this interpretation of your code and building up like a big structure from that. Now, after it does that, okay, so that's just the starting point. It turns out that it starts to get even more insane from there. What actually happens is once it makes that flow graph, it actually tries to annotate it with types. So it'll go in and say, oh, okay, I'm going to put types on this. And one of the things that happens is as it's scanning that, if it finds any new functions or any new features, it will recursively go do the same thing for those. So what it will do is start at the start of your program, make one of these graphs, and then it will sort of enter this discovery phase where it will just recursively explore all of the branches of your code, and then build up a huge graph structure from there. Does that sound about accurate from?
Yeah.
Yeah, okay, so it will sort of do that. It will do that until it sort of decides that it can't do anymore. Okay, so it's actually this recursive algorithm. It just sort of does it over and over and over and over again until it reaches essentially what's known as a fixed point, where like nothing changes, and then it's done with that. And so your head just completely explodes. Actually, I've been spending the last couple of days just trying to wrap my brain around like what in the hell is going on here. And it's like extremely non-trivial how they do this. So it turns out that that's about as far as I've gotten with it at this point. I think I'm out of time anyway. But that's sort of a small taste of sort of what these what is going on with Pypy and like how it's built. I mean, essentially you have this interpreter written in this subset of the Python language, and that interpreter is converted into C by directly analyzing its underlying bytecode structure. It's a little bit insane. It makes my head hurt, and so forth. One challenge in looking at this, if you're going to go exploring, is just figuring out what is going on. There's sort of Pypy interprets Python code. It's written in Python, but RPython is written in Python, and parts of RPython use Pypy. And like it's like at this point, it's sort of like just the head just completely explodes. I'm looking on the source, sort of figuring out what it is that you're actually doing. So that's kind of the end of this talk. It's a little bit incomplete. It's kind of work in progress. I just thought I'd sort of throw it out there and just sort of see I'm seeing like lots of really scared looks.
Now we'll present Lisp, which is he's gonna go in.
So David, can you now submit a bug report and a patch to Python?
No. I'm not even sure, like, I don't even know how many people look at this, one of the things that with this translation problem is just like, why does it take so long? And like, how would you fix it if it broke? Like if it breaks, I'm not even sure what to look at.
So this
I'm
is
just
just
trying to,
though,
I'm just trying to,
sort of the devilish problem with interpreted imperative, bytecode EMs, where if you're going to infer the code structure from bytecode, you have this problem.
yeah.
Which is there. And these guys have actually tackled it, which is pretty fantastic.
It's pretty amazing what they're doing, actually. I mean, like looking at it, it's insane. And like this whole bytecode interpretation thing that they're doing is just, it's quite crazy what they're doing there, because they're basically, I'll see if I can even explain. They're basically using the bytecode interpreter from Pypy, but they're doing all sorts of crazy workarounds to capture its state. Like what ends up happening is they like execute bytecodes, and then this capturing tool actually raises an exception to cause the whole thing to die. But then the exception gets caught, and then the piece of code that catches the exception goes in and grabs the state of the interpreter and like saves it, and then it will restart. Like it will basically
incrementally go down.
Yeah, it will like incrementally go through the codes, and it's like doing all this exception handling, and it's doing all this like bookkeeping of like states and frames and all this stuff, and it's just like.
So for things like scanning your code to detect errors, or it could be used for more than just generating code. It could be used to
maybe
potentially document things and draw pictures on.
I don't know. The thing that I think is amazing about it is the fact that it works off of like a live image of the code. Like it's not even looking at the source code. It's like it's entirely off of these like code objects. Just I don't know. I find that amazing.
So are they like simulating the runs so they know which path to optimize as the fast that runs over?
Without knowing more, I would just say yes. One thing I ran into, I wasn't able to reproduce it for this talk. Maybe I don't know, a coffee or something like that. I actually ran into a problem with RPython where I had some program that I was going to do like a performance test, and I tried to translate it, and the translation was just sitting there for like a really, really, really long time, like 5 minutes or like just sitting there doing nothing. And then it produced this code, and I realized that it actually did the calculation in the compiler and optimized it, and just printed out the result. I'm comparing this thing to Python. It's like, oh god, okay, the Python version of it takes like 2 minutes, and then the Pypy version takes like 0.01 seconds. You know, sort of the fact that it got completely optimized out. Like, you know, like a million iterations of some loop. I wasn't able to reproduce it for this talk. But,
So that would be faster than the C code.
yeah. I don't know. I probably just scared everybody off of Pypy. I am kind of interested though in just how this stuff works though. Kind of a gearhead.
How complete is it compared to CPython, say, 2.7? Can you run any CPython program in Pypy?
Depends on what package you use, what you're using.
Yeah, I think it depends on how many
Standard library
libraries.
stuff though?
What is standard?
I think it's at the 2.7 level now, isn't it, as of the last release?
Yeah.
And does it now port to the JVM and to?
I don't know the status of that. Do you know what the JVM for?
So JVM and .NET, I think those are the only ones. Backends exist for the RPython compiler, but the Pypy interpreter itself can't be compiled with them because it uses features of the language that those backends don't support. Yeah.
I don't know. Yeah, I think it just scared everybody.
But the Pypy itself is actually a little faster than Python.
Yeah, even a lot faster sometimes.
Do you think it's like
Not arbitrary Python code, RPython code.
like that Fibonacci?
Yeah, what's the option to do that? You know,
Multiply that by a lot. and it's
does it even?
Dash dash something equals JVM.
It isn't the
Yeah, this isn't in production anywhere, is it?
do you think it's like minus O JVM?
No. Try dash dash help, it's probably in there somewhere.
we build help.
Just run the C combiner for the help there.
Wow.
Minus.
That's some good help.
I feel like I'm looking at the output of configure help.
Yeah, it's pretty, somewhere in here.
I guess besides the
I
JVM.
don't know.
You just search for JVM in the output. Shove that into a file and grep it.
It's also supposed to make stackless Python, not just the
Yeah, except they don't show me the option. So just grepping for it there. I don't know. I'm out of time anyway, so that's just a little taste of what's going on in there. If you're going to go jump into the Python internal, I encourage it.
The rusty kernels are not nearly as scary as this, I swear. Mostly.
Okay.
So does it do stackless Python with no deal or just like a switch?
There's a stackless option.
Yeah, Pypy can be built with stackless enabled, and the next release that'll be the default. That doesn't mean there's no guild though, it's totally independent of guild.
You're not getting that lucky with the guild. All right, I'm done. So we'll have Alex come up here.
All right, so here's what we're gonna do. Stacy, we'll take a break in a second, but I also like the idea of introducing. We got a large group, not super large, but very manageable. And we're gonna introduce, but we're gonna do it in thirds. So we got 3 presenters, we got 3 lines of people here, and from stage left to this one, then this one. So basically, I want this whole column here to